Okay, welcome back. We're still on page 375 talking about the numerical probabilistic algorithm where I throw darts. I mean, obviously I'm not throwing darts, but it looks like I'm throwing darts. And then I count up the number that are inside versus outside. So randomly pick the points, throw them out there, and then the ratio. Since I know what the size of this square is, then it'll be a portion of that square. Okay, cool. The next one's talk about Monte Carlo integration. By the way, there are two things called Monte Carlo, and I don't want you to get confused. If this is a statistics course, we would have gone to this a heck of a lot more. I'm just warning you, there's several things called Monte Carlo. All right, just bear with me. All right, so this is kind of sort of like that. It's finding an area under the curve, kind of sort of like throwing the darts, except it's not an inscribed square. It's more like a plot. And then you could throw darts to figure out which is above and which is below the thing. Okay? Kind of sort of the same. Okay. The next one is probabilistic counting on page 377. This is a famous, parlor trick. Okay? I've seen this in several movies. It was a Sherlock Holmes movie, I believe it was, where they did this, where they had in a room of 25 people, what is the likelihood of having two people with the exact same birth date? And it turns out that if you have 25 people in the room, it's actually greater than 50%. It's greater than 50% that if you had 25 people, two of them are going to share the same birth date. And there's some math in here about how to do it. I'm not going to go in it, but it's pretty cool. It basically, it talks about 365 factorial divided by 365 minus the 25 factorial times 365 to the 25th power. And if you do the math, it comes out. So that is one of those techniques where if I asked you how many people would have to be in the room to get to 70% chance of having people with the same. See how you would do this thing? You basically, quite frankly, the way it would normally be done is you'd pick 20, you'd pick 25, and that didn't work. Pick 26 and 27, just kind of incrementally, guess. 27, 28, 29, 30. Okay, 30. Okay, if I had 30 people in the room, then the ratio is 70. So instead of trying to write an algorithm to figure it out, it's actually easier just to guess. The amount of effort it takes to guess is relatively low. And all you have to do is just run through the math with a loop until you find the right one. Not that big a deal. So this is one of those techniques where guessing is okay. And actually guessing is preferred. Okay. Monte Carlo algorithms on page 378. I told you there was two things here. So if you do a Monte Carlo algorithm, whatever that thing is, it always gives an answer, okay? This is a unique feature of a Monte Carlo algorithm. It always gives the correct answer. The problem is, it might not be all that great. It may be a really bad answer, but it'll give you an answer, for sure, okay? And so how good is the answer is the real thing. So if there's more than one possible answer, then you have no choice but to run it multiple times. So run it over and over and over and over and over until you come up with the correct answer. So let's just do an example of dice. So I'm playing dice. So at a casino. So 7 or 11 means I win. Okay. If I get 3, 5, 3, 4, 5, 16, 17, or 18, I lose, and everything else is just roll again. Okay. So there's 8 sides to a, how this works, right? 6 sides, and there's 2 of them, so it would be like, okay. I have seen this being done in Microsoft Excel. There's actually a Monte Carlo thing in Microsoft Excel. Now, rather than demo it, I have a really cool example on how to do this. So here's how to create a Monte Carlo model and forecast using Excel tables. And so I'm not going to go too much time into this, but basically what we're talking about is we have a spreadsheet and I'm basically trying to say a if I do this a couple of times, like 100 times, it's likely that I'm come up with the correct answer. So I don't know all the answers, okay? I don't. So here's my my projected income. My projected income is based upon sales, with gross profit, and then operating expenses and then taxes. But I really don't know what my operating expenses are going to be, and I really don't know what my sales are going to be. Okay? I don't know what these things are. I kind of sort of make some assumptions. This is 35%, this is 45%, etc. But I don't know that. So what I'm going to do is I'm going to create a table that just goes through and takes the 35 and makes it go from 25 to 60. And then I'm going to take the 45 and I'll make it go from 20 to 70. And then the 25, I'll make it go from 10 to 50. And then I just tell, okay, randomly pick a number for each one of the assumptions. And then just do it over and over and over and over. Sorry, randomly pick each one of the assumptions. And then when I get to the end, what is the most average one? My net profit after I've run this thing 100 times with random numbers each one. Because I really don't know what this is going to be next year. And I really don't know what that's going to be next year. So I start off with some assumptions, and then I vary on both sides of those assumptions, and then look at how these things are all related and come up with the total answer. Okay, is that kind of sort of making sense? I think my answer is going to be this, but I do a plus and a minus, randomly throw numbers at it, and then whatever one is the most average one is what I'm going to say. That's Monte Carlo analysis. Okay. So, determine the profit based upon estimated sales with min and max values. Run 100 times with random values, and then get an average of all the runs. Kind of cool. I kind of like this. This is kind of cool because if you knew in advance what your sales were going to be, you'd be a really wizard. But most people don't. And so they think, 45. But is it really going to be? So, we need to figure that out. Okay. I'm going to skip a little bit in the book and get to Las Vegas algorithms on page 380. Okay. Las Vegas ones, remember how the Monte Carlo one always gives you an answer, but it might not be that good? Well, Las Vegas ones never return a wrong answer. But it's possible they won't return an answer at all. It'll be like, sorry. So it'll never return something wrong. On the other hand, it might not return anything at all. So how useful is that? You kind of need to decide. Sometimes I want Monte Carlo because Monte Carlo means if I wanted better answer, I just throw a little bit more numbers at it. Instead of doing the forecasting model 100 times, I do it 1,000 times, okay? So it's your choice to say, I'd like to use Monte Carlo and I want to use 100 or 1,000 or whatever. On Las Vegas, then it's like, I'll run this a couple times, but it might not work for me. Okay. So here's an example. Remember the number of queens, okay? Using Las Vegas, I'll just randomly put a queen on the screen and see how it works. I'll just say, I'll put one here. Any problems? Nope. I'll put one here. Any problems? Nope. I'll put one here. Any problems? Nope. Now, when it gets to the end, is it possible for it to come up and say, I'm sorry, I couldn't find any solutions whatsoever? That is possible. That is very possible that the machine, well, maybe not for the end queens, but give me a break. It's possible that it basically says, I'm sorry, we can't solve this. Okay, cool. Again, there's an algorithm on page 381 and 2, but it's kind of a generalized algorithm. Don't bother to look at it. Okay. Sherwood algorithms on page 383. So this one always gives an answer, and it's almost always the correct answer. So you think, okay, that's pretty doggone cool. But that's not really the point to this one. What the point of this one is, it reduces the chance of having the worst case. In other words, statistically, most likely you're going to have that bell curve thing, okay? The bell curve thing. And so what Sherwood basically says is, let's just not consider the fact that it's going to be this outlier, because that's just not likely to occur. So I'm going to spend more effort on working on the center, so to speak, and less effort out here on the outside edges. Okay. Now, the way that works is, the reason why it's called Sherwood, because of Robin Hood. You know, rob from the rich and give to the poor. Except this case, I'm robbing from the outliers and giving to the more general. Okay, that's why it's called Sherwood, as in Sherwood Forest and the story of Robin Hood. I know, it's crazy as heck. All right, so let's just do one more time. So when the best and the worst case scenarios are difficult to determine, okay, where it's difficult to get this edge over here or this edge over here, this is a perfect scenario for that. Okay, example of using a binary search of 100 elements. If I started at 50, okay, which is normally the way you do a binary search, right? Started at 50. And if we guessed it right, let's say I guessed 25. Okay, 25, great. And we were right. Well, then this thing would go really fast, right? I mean, just 25. If I start at 50, go 25, boom. But what happens if I kind of sort of know that the outliers are not going to be all that important? So instead of starting at 50, I start at like 75. If my number was a 60, well, then starting at 75 would have better performance than starting at 50, right? Making sense? Okay. But if I'm wrong, well, then I'm really bad off. So in other words, if I set my guy up where I think I'm going to get somewhere in the vicinity of 60, well, then maybe I'll start instead of having my start guy starting at 50, I'll start at 60. If I am correct, woohoo! Perfect. If I am wrong, well, then it's going to take even longer than it did before. Okay? So I'm robbing from the rich to, see how this thing works? I'm thinking about, this is where I want it to be, and maybe I'll even just stop processing after 5 levels, okay? Or however many levels there are. If 1 in 100, I'll stop at 5 levels because I don't care about the tails, right? If you can't find it in 5, then we're not interested in the answer anymore. Okay, kind of makes sense. All right, let me explain this hopefully one more time. The goal is to reduce the time for the worst case, because the worst case really can't be done, and increase the amount of time. Increase the amount of time? Oh, let me start over. Reduce the amount of effort they're putting in calculating the worst case, and increase the amount of effort you're putting in working for the average case or the best case. Okay? Rob from the rich and give to the poor. Okay, let's just do a fancy comparison of what we learned so far on page 384. The numerical ones. So there's always an answer, and the answer is good. If you want a better answer, you just let it run longer. Monte Carlo. It always gives you an answer, but it might not be right. And again, if you want a better answer, you could let it run a little bit longer. Las Vegas it never gives you the wrong answer, but it might not give you an answer at all. And Sherwood is not really about getting the correct answer. It's not really about right and wrong. It's about speeding up the process on the hunch that your data is one way versus another. Okay? Okay, on page 385, change the subject. We're talking about dynamic programming. Typically, when you're writing a program, you have some data that you're inputting, and then you just go through, and you know exactly how many times things are going to go through, right? Loop counts, you can figure it all out. Well, with dynamic programming is, I have something in an array, and then I'm constantly updating the array. And as I'm updating the array now says, it says loop 10 times. And then I'm updating the array, and now it says loop 50 times. And I go, oh, okay. And then it says, okay, now we're looping 20 times. And it's like, okay, so you're updating the things that it takes to make the program work. So you don't really know how many loops you're going to have until after the program runs. Okay? That's it in a nutshell. Okay, we're coming up on the 15-minute mark.